Spacesuit engineers are developing technologies that would have been pure science fiction just a decade ago. Self-repairing materials represent one of the most promising breakthroughs, using polymer chemistry that allows suit fabrics to automatically seal minor punctures and tears without human intervention. These smart polymers contain microscopic capsules filled with healing compounds that rupture when the material suffers damage, releasing chemicals that bond together and restore structural integrity within minutes. The technology draws inspiration from biological healing processes, creating synthetic materials that can recover from damage just like living tissue repairs itself after injury. These self-healing capabilities become essential for Mars missions where astronauts will spend months on the planetary surface with no possibility of suit replacement or major repairs. Mars presents unique hazards including dust storms with particles moving at hurricane speeds, sharp volcanic rocks that can puncture conventional materials, and temperature swings of 200 degrees that cause repeated thermal stress on suit components. Self-repairing materials must function across these extreme temperature ranges while maintaining their healing properties despite exposure to cosmic radiation and chemical reactions with the Martian atmosphere. Mars missions will require suits that function as completely independent spacecraft capable of supporting human life for weeks at a time. Future Mars suits must include closed-loop life support systems that recycle air, water, and waste with near-perfect efficiency because resupply from Earth takes months and costs millions of dollars per kilogram. These life support systems will incorporate biological components including algae bioreactors that consume carbon dioxide and produce oxygen, bacterial waste processing systems that break down human waste into useful compounds, and water recovery systems that purify and recycle every drop of moisture from breathing, perspiration, and waste products. The closed-loop systems present engineering challenges that exceed anything attempted in current spacesuits. The biological components must remain stable and productive despite cosmic radiation exposure that would kill most Earth organisms. The recycling systems must operate reliably for months without maintenance or replacement parts while handling the full spectrum of human metabolic byproducts. These systems will incorporate multiple redundant pathways and backup processing methods to ensure astronaut survival even when individual components fail or become contaminated. Artificial intelligence integration in future suits will transform them into intelligent systems that monitor, predict, and respond to changing conditions faster than human reflexes can manage. Advanced AI systems will continuously analyze thousands of sensor inputs to predict equipment failures, health emergencies, and environmental hazards before they become dangerous. These AI systems will learn individual astronaut physiological patterns and behavioral preferences, optimizing suit performance for each crew member's specific needs and work habits. Machine learning algorithms will process data from suit sensors, astronaut biometrics, and environmental conditions to identify subtle patterns that indicate developing problems. The AI will predict when life support components need maintenance, when astronauts require rest breaks, and when environmental conditions might become hazardous. These predictive capabilities will enable proactive responses that prevent emergencies rather than simply reacting to problems after they occur. Enhanced mobility systems under development will finally eliminate the movement restrictions that have frustrated astronauts for decades. New joint designs use advanced bearing systems and flexible materials that provide natural human range of motion while maintaining perfect pressure integrity. These mobility improvements will enable astronauts to run, jump, and climb across planetary surfaces with confidence and efficiency that matches their Earthbound capabilities. The mobility advances incorporate lessons learned from robotics research and prosthetic development, using technologies originally designed for artificial limbs and industrial automation. Advanced actuators and sensor systems will provide powered assistance for heavy lifting and repetitive tasks while maintaining the natural feel of unassisted movement. These powered mobility systems will enable astronauts to carry heavier equipment loads and work longer hours without the fatigue that currently limits EVA duration and productivity. Future manufacturing techniques will revolutionize how spacesuits are designed, produced, and customized for individual astronauts. Three-dimensional printing technologies will enable on-demand production of suit components using materials available on Mars, the Moon, or asteroid mining operations. This manufacturing capability will reduce dependence on Earth-based supply chains while enabling rapid customization and repair of suit systems using local resources. Advanced manufacturing will also enable completely new suit architectures that current production methods cannot achieve. Integrated electronics, embedded sensors, and complex internal structures will be printed as single components rather than assembled from separate parts. This integrated manufacturing approach will create lighter, stronger, and more reliable suits while reducing the number of potential failure points that could compromise astronaut safety. Adaptive suit systems will automatically reconfigure themselves for different environments and mission requirements without requiring manual adjustments or component swapping. Shape memory materials will allow suits to change their profile and characteristics based on operational needs, becoming more flexible for scientific work or more protective during hazardous activities. These adaptive systems will incorporate multiple operational modes optimized for different environments, including vacuum, planetary atmospheres, underwater operations, and high radiation zones. The next decade will likely produce space suit advances that exceed everything achieved during the previous 60 years of human spaceflight. Current research projects are developing capabilities that will enable permanent human settlement of other worlds, multi-year deep space missions to asteroids and outer planet moons, and industrial operations in space that require sophisticated protective equipment. These advances will create suits that function more like wearable spacecraft than protective clothing, providing astronauts with the tools and capabilities needed to establish thriving human communities throughout the solar system. These technological achievements represent more than just engineering progress. They embody something fundamental about human nature and our relationship with the impossible. Space suits transform engineering challenges into exploration opportunities, proving that technical innovation can overcome the most hostile environments in the universe. These systems work because thousands of engineers dedicated their careers to solving problems that seemed impossible, turning science fiction concepts into reliable hardware that protects astronauts millions of miles from home. Every component represents decades of learning from failures, near misses, and the constant refinement of technology where anything less than perfection means death. The suits enabling today's missions are preparing us for tomorrow's destinations. Mars awaits, along with asteroids, distant moons, and places we haven't even imagined yet.